Hello, my name is Joshua Gonzalez, and today we're going to be going over the CSC 321 Mastery Extension Final Project. We're going to go over a little bit of how this project works, some of the motivations behind creating it, and some of the outputs. So let's dive right in. So overall, I wanted to create a secure file transfer between a client and a server. Um, Currently, I'm also taking this Intro to Computer Networking class, which we set up a TCP connection between the client and the server. And I thought it would be cool to have the client send over a file to the server using concepts that we learned in this class, such as AES CBC encryption and also um, SHA-256 hashing algorithms. So that's kind of the key idea. And let's dive right into how we did this. So first kind of topic of conversation was, how do we create a secret message between the client and the server that can be used for hashing and also creating the encryption? So we do this by using the Diffie-Hellman key exchange algorithm. This kind of works by first creating this public and private key pair using the elliptic curve Diffie-Hellman to generate key pairs for secure key exchange. This involves randomly selecting a private key and computing the corresponding public key by performing scalar multiplication of the private key with the point on the elliptical curve. So the public key can be shared openly while the private key is kept secret, is the whole idea. When the other party does the same, we can both compute a shared secret independently by multiplying their private key with the other party's public key. And this is because of the properties of the elliptical curve. So we create this public and private key pair here, right here, and we get it. And then now that we have our public and private key pair, we can then send it over the network. We can send the public key over the network to each other's parties. And this is what we do here. We send the public key over the network to the other party. So if I were the server, I would be sending my public key to the client, vice versa. The next thing we have to do is receive the public key that's being sent to us. So if I were the server, I would be receiving the client's public key. The next thing that we do is now derive this shared secret using our private key and the public key that we just obtained from the other party. So first we initialize this envelope with our private key, and then we set the key that we just received as the peer key or the public key from the other party, and then we can derive the shared secret. And this is where it is saved in the shared secret message variable. So at this point, we now have a shared secret between the client and the server that we can then use for encryption and hashing. So first thing we do in the client now we're in the client code. First thing we do is we're going to perform this file transfer. We call this file transfer function. And in the client, we read the file and save all of its plaintext into this variable plaintext, pretty much. We then connect to the server using creating a socket and then calling connect. And this is kind of the part where I use the code from our networking class. And so it was pretty useful here. And now that we have this derived secret, we can then hash it and use this hash for the encryption and hashing algorithm for the HMAC. So now that we got this AES key from the shared secret, we can now start encrypting. So let's go into that function. And pretty much what we do here is in AES, we need to have this initialization vector, and we're going to go to this little diagram here. How it works is that we XOR the plaintext with the initialization vector, and we get, and this also this key, and we get this ciphertext, and that ciphertext is then XORed again with the plaintext, and the next block of plaintext, along with the key, and then we get the ciphertext, and we keep, and this keeps going, and this is the CBC mode encryption algorithm that we use to encrypt our data. So let's go back. Here, when we encrypt it, we then get our ciphertext, and we save it into the ciphertext variable. With the derived key that we created using the public key and our private key, we can also compute the HMAC, hash-based message authentication code. And this pretty much is going to be compared with, it's going to be sent over with the ciphertext to be computed on the other end, on the server end, to ensure that there is integrity with the data being sent. We then build the protocol data unit, which is pretty much all the data that we are going to send to the server. And what we send is the initialization vector, we send the ciphertext, and we send the hash-based message authentication code to the server. All right. So now that data, the ciphertext, HMAC, and initialization vector, is all being sent to the server, and now we are in the server code. So here, we then receive the data that we just sent from the client, and pretty much extract the initialization vector, the ciphertext, and the HMAC. And what we do is we pretty much decrypt the ciphertext using that same derived key from before. So here we are decrypting it using the key that we derived before into this variable called plaintext, which after decryption it goes back to plaintext. And we write it now to a file, which pretty much completes the file transfer. Here we verified that the hash-based message authentication code, we can compute it again to ensure that the received hash-based message authentication code is the same HMAC as the one that was sent, so we know that any tampering with the data, we will know for sure based off this message here. This is pretty much exactly, we're ensuring that these two are the same, and that's kind of the key idea of using hashes, is to ensure that nothing was changed in the file being sent. All right, so now that the file transfer is pretty much done, we are going to then, I also add in this project a little attack that I want to perform on the server. The client pretty much goes into a loop and sets up 1,000 TCP socket connections to the server. And so this is going to pretty much ensure that, or overload the server that would basically replicate a distributed denial of service attack. The point of adding this kind of section to the project, I felt that even though we might have a super secure file transfer protocol or a file transfer algorithm, if we don't also cover our bases about the availability in the CIE triad, not just the confidentiality and the integrity portion of the CIE triad, we are still not secure as a system. And so I thought this was kind of cool and kind of important to point out, is that we kind of have to have all of our bases covered in security. It's not just two portions of the whole pillar. It's all the confidentiality and security, and also the availability, because if the server goes down, nobody can talk to each other. Okay, I think at this point we can then start running the code and kind of see how it's working. So that's what we're going to do now. Let's see. We're going to create, so I'm going to cd mastery extension. Okay. And we're going to run server. So now that we are running the server here, going here, we're going to cd into this Okay. Now, so what we are going to do is the point of this kind of demonstration. This is the file that the server is going to write into, and this is the file that the client is going to send. So ideally what should happen is that the client reads and sends the ciphertext of this plain text here, to the server, and after that is completed, the server should populate this file with what is in here, secure or ensuring that we get the correct file over to the server. So let's run that right now. Client. Yep, and it does work. So that was pretty cool. And kind of going through some of these outputs that are here. So here I kind of printed out the public and the derived, or the public key here, and also the derived shared secret. And we can see if we look at this line right here, the derived shared secret, this line right here, and also the server's derived shared secret, you can see that they're the same. And this is the whole point of using the Diffie-Hellman to get this derived shared secret that can be then used to for hashing and encryption. All right, the last thing that we're going to kind of touch on here is we're going to run the server again. And now we're going to perform this attack, this little code. So let's use this. Oh, I think I'm here. Okay, clear. Oh. And we're going to use this little flag called attack. So kind of same thing. We're going to first do the file transfer. We know that that worked. And now what we're going to do is we're going to open up a bunch of TCP connections that we can see here. So this is us performing this DDoS attack and just constantly trying to open up TCP sockets to the server. And then eventually we can see that all these connections are refused. And so we get a few good ones, and then all of a sudden all these connections are refused. And so let's take a look at what happens on the server side. So here we see these last few messages of all these attempts that the server is trying to connect to these clients that we looped. We see that the server basically stopped working, exiting, causing this print statement here. Server under attack, too many connections, crashing now. And that is because I added the server code. Let's see. If the connection count, we count every single connection that we get. If the connection count is greater than max connections, I believe I said to 50, then this is kind of simulating what would happen in a real life DDoS attack, is that we get too many connections and the server pretty much shuts down. So yeah, that was my CSC 321 Master Extension project. I hope you liked it. Thank you.